If you could climb into a rocket tomorrow and fly to any planet you liked, how long would you be gone? Most people guess weeks, maybe a few months. For some of these worlds, you'd be signing away 10 years of your life. And for one of them, you'd be gone even longer than that, despite it being one of our closest neighbors. That's what nobody explains about getting around out there. Distance is only half the story. Some short trips are painfully slow, some enormous ones are surprisingly quick, and a few can only begin on a handful of days every couple of years. So let's go through every planet in order and find the real numbers. By the end, you'll know which one is the hardest place in the solar system to reach, and why it isn't the one you're picturing right now. Now get yourself comfortable, hit subscribe, we begin. Almost every one of us met the solar system for the first time as a picture, a poster on a classroom wall, or a page in a book. The sun pushed into one corner, and then the planets, laid out in a neat row, each one a little further along, each one comfortably within reach of the next. Mercury, Venus, Earth, Mars, then the great banded giants, and finally the two blue worlds at the edge. That picture taught us the order of the planets. It also taught us something that was never true. The spacing on that page was never physics. Printers and illustrators face a simple problem. The real solar system does not fit on paper, so they compress it. They shrink the gaps between the outer worlds by factors of hundreds, because otherwise Neptune would need to sit in another building. What we were handed was not a map. It was a graphic design decision, made for the sake of the page, and quietly absorbed by all of us as fact. Let's start with what that page actually removed. Picture Earth shrunk down to a tennis ball, resting in your palm, about 6.5 centimeters across, roughly 2.5 inches. Hold that scale steady, because everything else has to shrink by exactly the same amount. At that scale, the sun becomes a sphere a little over 7 meters wide, around 24 feet, the width of a modest house, and it sits nearly 800 meters away, half a mile. You would have to walk for 10 minutes to reach it. Mars would be a smaller ball, roughly 1.25 kilometers from that sun, 3/4 of a mile, still walkable. And Neptune? Neptune would sit almost 24 kilometers away, nearly 15 miles. From the tennis ball in your hand, you would need to drive for half an hour to find it. That is the same solar system printed on the poster. Same worlds, same order. The only thing that changed was honesty about the gaps. Light tells the same story in a different language. Sunlight takes 8 minutes and 20 seconds to cross the distance to Earth, meaning the light warming your skin on a summer afternoon left the sun before you decided to step outside. That same light needs 4 hours and 6 minutes to reach Neptune, the fastest thing in the universe, moving at 300,000 kilometers per second, about 186,000 miles per second, and it still spends most of a working day crossing our own solar system. Nothing we build travels anywhere near that fast. Ask people how long a trip to Mars would take, and the answers cluster somewhere around a few weeks. A month maybe, something like a long sea voyage. The real floor is closer to 7 months. Not the comfortable estimate, the floor. The best that orbital mechanics allows without extraordinary expense. And here is where the question contains a hidden trap. Most people assume the delay comes from the distance, that Mars is simply far and far takes time. That assumption feels obvious. It is also wrong, and understanding why it is wrong is the key to everything that follows. Distance is not the currency of spaceflight. The currency is something called delta V, a phrase that sounds technical and means something almost embarrassingly simple. Delta V is the total amount of velocity change a spacecraft can produce before it runs out of propellant. Not how far it can go, how much it can change the way it is moving. Think of it less like the fuel gauge in a car and more like a bank balance you can never top up. Every push, every turn, every attempt to slow down, each one is a withdrawal. When the balance reaches zero, the spacecraft keeps moving forever, but it can no longer choose where. Mission design is the art of spending that account wisely. Nothing else. And this changes what a launch actually is. Right now, sitting wherever you are, chair beneath you, floor solid under your feet, Nothing about you apparently in motion. You are traveling around the sun at 29.8 kilometers per second. That is roughly 107,000 kilometers per hour, or about 66,000 miles per hour. In the time it takes to read this sentence, you have moved further than the length of most countries. Every spacecraft ever launched inherited that speed for free, simply by being built on a planet that was already moving. So a rocket never launches from rest. Nothing does. A spacecraft leaving Earth is not starting a journey from a standstill. It is already in orbit around the sun, traveling at enormous speed, and all it can do is modify that orbit, nudge it wider, nudge it tighter, change its shape. Spaceflight is not travel. Spaceflight is orbit editing, which leads to something that surprises almost everyone the first time they hear it. Rockets do not aim at planets. If you fired a spacecraft directly at Mars, you would arrive at a patch of empty space, weeks or months after Mars had already moved on. Mars will not wait. Instead, engineers aim at a location where nothing currently exists, the point where the planet will be when the spacecraft finally gets there. The same instinct a footballer uses passing to a teammate already running. You never aim at the person. You aim at the space they are about to occupy. The cheapest way to do this has a name, and a very old one. Imagine an ellipse, a stretched circle, with the sun sitting off to one side. One end of that ellipse just touches Earth's orbit. The far end just touches the orbit of Mars. Fire the engines once at Earth to climb onto that ellipse, coast the whole way around, then fire once more on arrival to settle into the new orbit. 2 burns. Everything between them is silence and falling. That path is called a Hohmann transfer, named for Walter Hohmann, a German engineer who worked out the mathematics in 1925. He published it decades before any rocket flew, before anyone had launched a single object out of the atmosphere. He was describing the geometry of journeys that no human being would be able to attempt for another 35 years. The Hohmann transfer is the cheapest route between 2 orbits. It is also, almost always, the slowest. From Earth to Mars, that ellipse takes roughly 259 days of pure coasting, around 8.5 months. Engines off. No thrust. Just an object falling along a curve, exactly as a thrown stone falls, except the stone in this case has been thrown across 99 million kilometers of vacuum. Faster paths exist. They always cost. Every shortcut in space is bought with propellant, and propellant is not free, because propellant has mass, and mass must itself be accelerated. Konstantin Tsiolkovsky, a nearly deaf Russian schoolteacher working largely alone, wrote down the relationship in 1903. Engineers today call the result the tyranny of the rocket equation, and the tyranny is this: to go faster, you need more fuel, and that extra fuel must itself be carried, which requires more fuel to carry it, which requires more fuel again. The cost does not climb steadily. It climbs exponentially. The consequences show up in the hardware in a way that borders on absurd. The Saturn V, the largest rocket ever flown successfully, stood on the pad as roughly 85% propellant by mass. The actual useful payload rarely exceeded 4% of the whole machine. The astronaut Don Pettit, writing for NASA, found the comparison that makes this land. A soda can is about 94% liquid and 6% aluminium, and you can crush one in your hand without effort. The Space Shuttle's external tank was 96% propellant and 4% structure. We build rockets to the same fragility as drinks cans, then ask them to survive the most violent controlled event in engineering. That is why speed is rationed, not because we lack ambition, because physics charges compound interest. So mission designers need a way to know precisely how expensive any given departure would be. That number is called C3, launch energy. In plain terms, C3 measures how much energy a rocket must give a spacecraft beyond simply escaping Earth. A low C3 means an easy departure. A high C3 means a departure that only the most powerful rockets in existence could even attempt. C3 is the gatekeeper. It decides not when you launch, but whether you can. To visualize it, engineers build something called a pork chop plot. Picture a chart with every possible departure date running along one edge and every possible arrival date along the other. Every combination of the two gets shaded according to how much energy it would demand. What emerges looks strikingly like a topographic map of a mountain range, contour lines wrapped around high ground and scattered among them a few deep low-lying basins. Those basins are the launch windows, not calendar dates chosen by committee, valleys in an energy landscape carved by the geometry of two moving worlds, and they close. Earth completes a lap of the Sun in 365 days. Mars takes 687. Because the two run at different speeds, they only return to the same relative arrangement every 780 days. 25.6 months, call it 26. That is the entire schedule of Mars exploration. Not a policy. A gate set by orbital geometry, opening for a few weeks and then sealing for over 2 years. Think about what that means for the people who build these machines. A spacecraft that misses its valley does not launch a month late. It sits, finished, tested, flight ready, worth hundreds of millions, in a clean room, doing nothing, while 2 entire years pass. Engineers grow older, budgets get re-argued, careers move on, and the hardware waits, sealed and silent, for the sky to allow it. The universe does not accept late applications. One more piece completes the picture, and it feels like cheating. The same engine, burning the same propellant for the same duration, gives you more useful energy when it fires deep inside a gravity well while already moving fast. Hermann Oberth described this in the late 1920s, and we call it the Oberth effect. The intuition comes from a playground swing. Push at the top of the arc, where the swing hangs almost still, and you achieve very little. Push at the bottom, where it is racing through, and the same push carries far more effect. Speed makes force count for more, which explains a behavior that otherwise looks insane. Spacecraft frequently dive toward a planet, falling inward, gaining speed, dropping deeper into gravity, and only then light their engines. They deliberately fall in order to leave more efficiently. Now these trades stop being abstract because eventually we intend to put people inside these trajectories, and the mission designers have not agreed on how. One camp favors what they call conjunction-class missions. Cheap fuel, minimum energy, roughly 180 to 210 days out, the same coming home, and, because the return window will not open sooner, around 500 days sitting on the Martian surface. Total mission time, about 900 days, nearly 2.5 years, but the crew spends most of it standing on a planet, with a world beneath them absorbing some radiation from below. The other camp argues for opposition-class missions. Total time drops sharply, somewhere between 400 and 750 days, but the surface stay collapses to a month or two. Worse, one leg of that journey has to swing inward, often nearly as close to the Sun as Venus's orbit, to compensate for the poor alignment. More heat, more solar radiation, far more time floating in open space with nothing but hull between a human body and the galaxy. Neither side is being careless. Conjunction buys shielding and science and charges 900 days of exposure to get it. Opposition buys a shorter absence and charges a hotter, harsher, more energetic road. Both camps are weighing human lives against propellant, and the honest answer is that the disagreement has not been settled. Because the medical evidence needed to settle, it does not fully exist yet. And there is one more option, stranger than the rest. In the late 1980s, the mathematician Edward Bell Bruno began exploring what happens in the chaotic regions, where the pull of 2 or 3 bodies almost cancels out. In those places, a spacecraft can be nudged, barely, and drift into capture almost for free, riding the combined gravity of Sun, Earth and Moon the way a small boat rides an ocean current, rather than fighting across it. In 1991, Japan's Hitten spacecraft became the first to fly such a path, after Bell Bruno and James Miller at NASA's Jet Propulsion Laboratory salvaged a mission that lacked the fuel for anything conventional. The direct route to the Moon takes about 3 days. Huyton's route took 5 months. NASA flew the technique again in 2011 with Grail, twin spacecraft that launched on the 10th of September and did not reach lunar orbit until New Year's Eve. 3.5 months to cross a gap that Apollo crews closed in 3 days. Each spacecraft travelled roughly 4 million kilometres, about 2.5 million miles, around 10 times the actual Earth-Moon distance, looping out past the point where the Sun's pull and Earth's pull balance and drifting back. The reward was around 130 meters per second of saved velocity change. That saving became science instruments. They bought propellant with time. In spaceflight, that exchange is always available, and the rate is always brutal. So the shape of the whole problem is now visible. Every trajectory ever flown, and everyone still on the drawing board sits somewhere inside a three-way trade: propellant, time, and human risk. Push down on one, and the others rise. Save fuel, and the journey stretches. Shorten the journey, and either the rocket must grow beyond anything we can build, or someone absorbs more radiation to make up the difference. The solar system does not sell speed, it rents it, and the price is paid in years. Which brings us back to that poster on the wall, and to the last lie it told. The page suggests a hierarchy of difficulty. The outer worlds look hard because they sit far to the right, at the edge of the paper. The inner worlds look easy. They are right there, crowded near the sun, close to us, first in the row. But remember what actually costs money out here. Not distance, velocity change. Falling toward the sun means gaining speed, enormous, relentless, unavoidable speed. And every kilometre per second you gain on the way down must be violently thrown away again on arrival, or you simply fall past your destination and keep going. Going inward is not easier than going outward. Going inward is harder. And the single most expensive destination in the entire solar system, more demanding in pure delta V than an object at the edge of the known planets, is the small grey world sitting closest to the sun on that classroom poster. The one that looks like the shortest trip of all, Mercury. The smallest planet, the nearest to the sun, and by every instinct we possess, the one that should have been simplest. At its closest, Mercury comes within about 77 million kilometres of Earth, roughly 48 million miles. Compare that to Neptune, sitting more than 4 billion kilometres out, and the difference feels decisive. One is a neighbour, the other is a rumour, and yet we have orbited Mercury exactly once in the whole history of spaceflight. The reason has nothing to do with how near it sits. The reason is that reaching an inner planet means doing something no engineer ever wants to do. It means falling. Here is the part that breaks most people's intuition, so it's worth slowing down. Leaving Earth for the outer solar system means climbing. You fight the sun's gravity the entire way, and the sun quietly steals your speed as you go. By the time a spacecraft reaches Jupiter, it has been decelerating for years without touching its engines. Arriving slow is the natural outcome. Going inward reverses every part of that. Aim a spacecraft toward the sun, and gravity stops resisting you and starts helping. Not gently, constantly. Every hour of the journey the sun is pulling harder, and every hour the spacecraft is moving faster than it was before. Think of a bicycle at the top of a long hill. You never touch the pedals, you simply let go. And the further you roll, the faster you go, and the harder it becomes to stop. Now imagine that hill has no bottom, and it steepens the whole way down. You do not coast gently into the inner solar system. You arrive at it like a stone. And a spacecraft that arrives too fast does not enter orbit. It flies straight past and keeps going. Forever. Now put numbers on the problem, because the numbers are where the horror lives. Earth carries us around the sun at 29.8 kilometers per second. Mercury, much closer in and whipped along much harder, travels at about 47.4 kilometers per second, roughly 60% faster. So a spacecraft that has fallen all the way down to Mercury's orbit does not merely need to be in the right place. It needs to match a world that is moving through space some 17.5 kilometers per second, differently from where it began, around 63,000 kilometers per hour, or roughly 39,000 miles per hour, of raw velocity that has to be found or thrown away. A high-velocity rifle bullet leaves the barrel at about 1 kilometer per second. The correction alone, before any of the rest of the mission, is more than 17 times that, which produces a result that sounds like a misprint the first time you hear it. Measured in pure velocity change, settling into orbit around Mercury costs more than reaching Pluto. The nearest planet is, by the only currency that matters out here, the most expensive destination we have, and Mercury takes away the one tool that might have helped. At Mars, at Venus, at Earth, a spacecraft has a free break available. Dip into the upper atmosphere and the air pushes back. The same firm shove you feel putting a hand out of a moving car window, multiplied enormously. Engineers call this aerobraking, trading speed for heat and paying for it with nothing but a heat shield. Mercury has no air to shove against. Its atmosphere is barely an atmosphere at all, a whisper of atoms blasted off the surface by sunlight and solar wind, thinner than the best vacuum any laboratory on Earth can produce. A hand passed through it would feel absolutely nothing, so every last fragment of that velocity mismatch has to be paid for with rocket engines. Fuel, carried from Earth, accelerated the whole way. But that is not the only thing waiting. Sunlight at Earth delivers about 1,360 watts to every square meter, roughly the output of a domestic kettle spread over an area the size of a small tabletop. At Mercury, that figure climbs to somewhere between 6,000 and 14,000 watts per square meter, depending on where the planet sits in its stretched egg-shaped orbit, up to around 10 times as intense. Imagine 10 kettles at full power poured continuously onto every single square meter of a spacecraft's skin, with nowhere to dump the heat except to radiate it slowly back into the dark. The surface below is worse. Mercury's day side reaches roughly 430 degrees Celsius, around 800 Fahrenheit, hot enough to melt a block of lead and leave a puddle. One of the engineers who built hardware for that environment described the challenge simply. They were flying into a pizza oven. So this is the shape of the problem, a destination that demands more velocity change than the outer edge of the planets, offers no atmospheric break whatsoever, and cooks everything you send. Let's look at what we actually managed to do about it. On the 3rd of November, 1973, an Atlas Centaur rocket lifted a spacecraft called Mariner 10 off a pad at Cape Canaveral. Mariner 10 carried a technique that had never been flown. 12 years earlier, in 1961, a young mathematician named Michael Minovich, working at NASA's Jet Propulsion Laboratory with borrowed computer time, had worked out that a spacecraft passing close to a planet could steal a sliver of that planet's orbital motion and change its own path for free. No propellant, just geometry. Mariner 10 became the first mission ever to use it on the way to another world. On the 5th of February, 1974, it swept past Venus, and Venus bent its path inward. 7 weeks later, on the 29th of March, it passed Mercury, a journey of about 5 months from Earth. Then came the Italian mathematician Giuseppe Colombo, who noticed something in the numbers that the mission designers had missed. Mariner 10's new orbit circled the Sun in exactly the time Mercury took to go round twice, which meant the encounter would repeat. Every 6 months, the spacecraft and the planet would meet again in the same patch of space. 3 flybys followed: March 1974, September 1974, March 1975, and then, on the 24th of March, 1975, with its maneuvering gas exhausted, controllers switched the transmitter off. Mariner 10 never entered orbit. It never tried. Slowing down enough to be captured was so far beyond what the mission could afford that nobody put it on the table. And then, for 30 years, nothing. Nobody went back. On the 3rd of August, 2004, NASA launched Messenger, a spacecraft about the size of a large office desk, more than half of whose launch mass was propellant. Think about that ratio for a moment. Of roughly 1,100 kilograms sitting on the pad, around 600 kilograms was fuel, and the single burn that finally dropped it into Mercury orbit consumed nearly a third of everything it had launched with. This machine was, in a real sense, a fuel tank with instruments bolted on. Even that was not enough on its own. Messenger had to spend years bleeding off speed the only way physics allowed, by falling past planets and letting their gravity take a bite each time. 1 flyby of Earth, 2 of Venus, 3 of Mercury itself, each one shaving away a little more velocity, each one setting up the next. It entered orbit on the 18th of March, 2011, 6.5 years after launch. Along the way, it had looped the Sun more than 15 times and travelled 7.9 billion kilometres, 4.9 billion miles, enough to fly from Earth to the Sun and back more than 26 times over. All of it to close a gap that, at its narrowest, measures 77 million kilometres. The spacecraft flew more than 100 times the straight-line distance to its destination. That is what the inner solar system charges, which brings us to a spacecraft currently in flight, named, fittingly, after the man who spotted Mariner 10's hidden resonance. Bepi Colombo, built jointly by Europe's ESA and Japan's JAXA, launched on the 20th of October 2018. 2 orbiters riding together on a transfer module driven by ion engines, aimed at a planned arrival in December 2025. Then, in April 2024, engineers found something wrong. The transfer module's electric thrusters had stopped receiving full power, traced to unexpected electrical currents in the path between the solar array and the unit that distributed that power. Months of investigation followed. The thrusters could be run, but not hard enough. They could not stop the spacecraft in time. The flight dynamics team at ESA rebuilt the trajectory instead, flying the remaining Mercury passes closer to the planet to squeeze more braking out of its gravity. The science survived intact. The schedule did not. Orbit insertion moved to November of this year, pushing the total cruise to roughly 8 years. 9 planetary flybys in all, 1 at Earth, 2 at Venus, 6 at Mercury. 9 separate encounters, each one required simply to slow down. As you listen to this, that spacecraft is still falling, still shedding speed, still months away from the moment it either enters orbit or does not. Venus sits between Earth and Mercury, and it is genuinely kinder. The velocity mismatch is smaller, the fall is shallower, and Venus has a thick atmosphere, which gives engineers back the break that Mercury denies them. The record shows it. Mariner 2 launched in August 1962 and reached Venus in about 110 days, under 4 months, and humanity's first successful mission to another planet, at a time when most spacecraft still failed on the launch pad. The Soviet Venera landers typically crossed in 4 to 5 months, one after another, through the 1970s and 80s. But now hold 2 facts side by side. Mariner 2 crossed in 110 days in 1962. NASA's Magellan spacecraft launched from the cargo bay of Space Shuttle Atlantis on the 4th of May, 1989, 27 years later, with vastly better technology, did not arrive until the 10th of August 1990. 15 months, nearly 5 times longer. How does a mission get slower as the technology improves? Because Mariner 2 only had to pass Venus. Magellan had to stop there. Released into low Earth orbit by a shuttle, boosted by a modest solid fuel upper stage, it had nothing like the launch energy for a direct run, so it looped the Sun 1.5 times, arriving at the precise moment when Venus and the spacecraft were moving slowly enough relative to each other for capture. The extra year brought nothing but geometry. Venus has become the pivot the entire inner solar system turns on. Galileo used it, Cassini used it, Messenger used it twice, and NASA's Parker Solar Probe used it 7 times. Each Venus pass stripped away a slice of Parker's sideways motion, which sounds like the opposite of what a record-breaking spacecraft would want, but removing sideways speed is exactly how you fall closer to the Sun, and falling closer to the Sun is how you go fast. On Christmas Eve, 2024, After its final Venus flyby, Parker Solar Probe swept through the Sun's outer atmosphere at 692,000 kilometers per hour, 430,000 miles per hour, 192 kilometers every second. At that speed, you would cross from New York to Tokyo in under a minute, London to Sydney in about 90 seconds. Nothing built by human hands has ever moved faster, and none of that speed came from an engine. Venus arranged it, and the Sun's gravity did the rest, which leaves mission designers with an uncomfortable dependency and a disagreement that has not been settled. Earth and Venus return to a favorable alignment only every 19 months or so. Every inner system mission that leans on a Venus assist is therefore locked to that clock, and to a chain of encounters where a single missed pass can unravel everything downstream. One side argues that the arrangement is simply good engineering. Gravity is free, propellant is not, and refusing free energy to save a few years makes no sense. The other side argues that these chains stretch cruises to 8 years and beyond, stack up single points of failure, and that maturing electric propulsion should be used to loosen the dependency rather than deepen it. Both positions are held by serious people. Neither has won. And there is a second argument, sharper still, about what is actually in Venus's clouds. In 2020, a team led by Jane Greaves reported an absorption line in Venus's atmosphere that they attributed to phosphine, a gas that, on Earth, essentially only life produces. Other groups pushed back hard, arguing the signal came from statistical artifacts in the data processing, or from sulfur dioxide sitting at almost exactly the same frequency, or that independent observations showed no phosphine at all. The original team answered each objection. Follow-up campaigns using the James Clerk Maxwell telescope have recovered the signal repeatedly. The separate ALMA detection has not held up nearly as well. 6 years on, the honest position is that nobody knows, and confirming it almost certainly requires going there, which means waiting for the window. Every extra year of cruise carries a hidden bill. A spacecraft looping the inner solar system is not resting. Solar radiation is grinding at its electronics, thermal cycling is working at its seals, and its plutonium or its batteries are quietly declining. Messenger spent 6.5 years aging before its science began. Bepi Colombo will have spent 8. The machine that arrives is never the machine that launched. So set the record side by side and let the contradiction land properly. The first spacecraft to reach Jupiter, a world more than 5 times further from the Sun than Earth, out past the asteroid belt, in the opposite direction entirely, crossed that distance in under 2 years. Messenger took 6.5 years to reach a planet that can sit 77 million kilometers away. The nearby worlds took longer than the giant. That poster on the wall had the order right and the difficulty exactly backwards. Distance was never the map. Energy was. And on an energy map, Mercury drifts to the outer edge of the solar system, while Jupiter moves closer in. But between those two extremes sits one more world. Not the hardest to reach, not the easiest, just the one we keep going back to again and again, where the alignments come around on a schedule so rigid that entire nations have built their space programs around it, and where missing the window by 3 weeks means waiting more than 2 years to try again. Mars. Mars is the one world where orbital mechanics stopped being an engineering detail and started dictating government budgets. No other destination does this. Nothing else in the solar system takes a gate that opens for a few weeks, slams shut for more than 2 years, and forces multiple nations that agree on almost nothing, to build to the same deadline. But the gate does not care who is ready. In the summer of 2020, 3 separate spacecraft left Earth inside a span of 2 weeks. The United Arab Emirates sent Hope, its first interplanetary mission, on the 19th of July. China sent Tianwen-1 on the 23rd. NASA sent Perseverance on the 30th. 3 programs, 3 continents, 3 entirely different sets of political pressures and engineering cultures, and all of them queuing at the same doorway in the same fortnight because physics had handed all 3 the same appointment. Nothing about that was coordination. Nothing about it was rivalry either, not really. Every one of those teams had spent years working backwards from a date that no human being chose. Modern orbiters and landers need 7 to 9 months to make the crossing. Perseverance took 203 days. And here's the thing, most people don't realize about those months. Almost nothing happens during them. The spacecraft is not flying. Its engines are silent for essentially the entire journey. What looks like a voyage is really one enormously long fall. A stone thrown across the inner solar system, arcing along a curve that was fixed at the moment the upper stage shut down. Every few weeks, controllers fire tiny thrusters for a handful of seconds to trim the aim. Nudges. The kind of correction you make with a fingertip, not a shove. Perseverance covered 472 million kilometers that way, 293 million miles. Roughly the distance you would cover driving around the Earth's equator 11,000 times. None of that distance was a straight line. Mars was never where the rocket pointed. Mars was where the rocket's aim intersected the future. Radio signals cross that gap at the speed of light, and even light struggles. Depending on where the two planets sit in their orbits, a message from Earth reaches Mars in anywhere from about 3 minutes to about 22 minutes. One way. Ask a question at the widest separation, and the earliest possible answer arrives roughly 44 minutes later. Imagine holding a conversation like that. You speak, you make lunch, you come back and listen. Nothing you say can ever be a response to something happening now, only to something that finished happening a long time ago. And every 26 months or so, even that becomes impossible. When Mars passes behind the Sun as seen from Earth, an alignment called solar conjunction, the Sun's outpouring of charged particles corrupts anything sent through it. Commands can arrive scrambled, so mission teams stop sending. For roughly 2 weeks, every spacecraft at Mars runs on instructions loaded in advance, doing safe, simple work entirely alone. Then the geometry shifts and controllers start talking again. Which brings us to the sharpest edge of the whole problem. Entry, descent and landing takes about 7 minutes. In that time, a spacecraft arriving at nearly 20,000 kilometers per hour, around 12,500 miles per hour, fast enough to cross the United States coast to coast in roughly 12 minutes, has to come to a complete gentle stop on a surface it has never touched. No human being can help. Not one command can be sent in time. Place yourself inside that aeroshell for a moment. The first thing that happens is heat. Compressed gas piles up ahead of the heat shield and glows, and the outer surface climbs toward 1300 degrees Celsius, around 2400 Fahrenheit, close to the temperature at which steel itself begins to melt. Around you, the air ionizes into plasma, and that plasma does something unnerving. It blocks radio entirely. At the most violent moment of the descent, the spacecraft cannot say a word. Then a parachute fires open at supersonic speed. The heat shield drops away. Radar reaches down and finds the ground. The rocket-powered descent stage lights, slows to walking pace, and lowers the rover on cables like a crane setting down a piano, then cuts those cables and flies clear. Hundreds of events, each one required, each one autonomous. Now the part that stays with you. During Perseverance's landing on the 18th of February 2021, the one-way signal delay stood at more than 11 minutes. So when the room at JPL heard entry interface, the spacecraft touching the top of the atmosphere, that had happened 11 minutes earlier. The full descent lasts 7, which means that at the instant controllers learned the landing had begun, the rover had already been sitting on the surface of Mars for 4 minutes, intact or scattered across a crater floor. Decided. Finished. Everything the world watched that afternoon was a recording of a fate already sealed. The cheering was not hope, it was reaction to a past nobody could reach. Landing is only the beginning of the cost. Curiosity touched down in August 2012, and human beings have been writing its instructions day after day ever since. More than a decade of daily planning for a machine on another planet. But a Martian day does not match ours. A Sol runs 24 hours, 39 minutes and 35 seconds. roughly 40 minutes longer. That sounds harmless. It is not. To work alongside a rover that sleeps at Martian night and wakes at Martian dawn, mission teams shift their entire lives onto Mars time, usually for the first 90 sols after landing. Every single morning, the alarm goes off about 40 minutes later than the day before. Follow that forward. After 10 days, you are more than 6 hours out of step with everyone you know. After a month, you are almost exactly half a day inverted. Eating breakfast at midnight, driving home as your neighbours leave for work, watching the sun through blackout curtains that never come open. During the Spirit and Opportunity missions, JPL issued staff wristwatches that ran deliberately slow, and people wore them beside their ordinary watches, one on each wrist. Sleep researchers from Harvard and Brigham and Women's Hospital came to JPL to study what this does to a body. They found most team members chronically sleep-deprived within the first few weeks. Deborah Bass, who worked the rover missions, described it simply: jet lag that never resolves, because the destination keeps moving. The human circadian rhythm cannot lock onto a target that drifts, so it never locks on at all. Part of the price of exploring Mars is paid in other people's sleep, and even after all of that, the waiting, the falling, the 7 minutes, the inverted lives, Mars remains the place where our machines go to die. Roughly half of every mission humanity has ever aimed at Mars has failed. By some counts, more than half. No other destination has a record like it. The Soviet Union carried the worst of it. Mars 2 struck the surface in 1971 and became the first human object to reach Mars by crashing. Mars 3 landed intact days later, began transmitting, and stopped after about 20 seconds, returning a single fragment of an image that nobody has ever been able to interpret. Mars 6 fell silent during descent in 1974. Mars 7 missed the planet completely. NASA's turn came later and hurt just as much. Mars Observer went quiet on the 21st of August, 1993, 3 days before orbit insertion, after 11 months of flawless cruise. Investigators concluded a fuel pressurization tank had almost certainly ruptured. The spacecraft had cost around $800 million, nearly 4 times its original budget, and nobody ever heard from it again. Then 1999, which remains the hardest year in the record. Mars Climate Orbiter arrived in September. One engineering team's software produced its results in pound force. The navigation team receiving those numbers assumed newtons, a different unit of the same quantity, differing by a factor of about 4.5. Nobody caught it. The spacecraft came in far lower than intended, entered an atmosphere it was never built to touch, and was gone. The error cost around $193 million. Weeks later, Mars' polar lander went down near the southern pole. The leading explanation is almost unbearable in its smallness. As the landing legs snapped into position, the shock produced a spurious signal that the flight software read as touchdown. The engines shut off. The lander was still roughly 40 meters above the ground, about the height of a 12-story building, and simply fell. Japan's Nozomi failed differently. It failed slowly. A flawed Earth flyby in 1998 left it short on fuel. Engineers designed a 5-year looping recovery trajectory to try again. Then, in April 2002, a solar flare damaged its electrical system. Its hydrazine froze in the lines. In December 2003, after half a decade of patient improvisation, controllers let it drift past Mars and gave up. Here is what those losses actually mean, and it goes far beyond the money. Lose a spacecraft anywhere else and you rebuild. Lose one at Mars and you rebuild, and then you wait, because the gate has already closed behind you. Work the timeline honestly. A failure investigation takes months. Redesign and rebuild takes longer. Requalification and testing longer still. And when the hardware is finally ready, the calendar decides when it flies. Realistically, from the moment a Mars mission dies to the moment its replacement leaves the pad, 4 to 6 years pass. No other field of engineering operates like this. A failed bridge is rebuilt. A failed aircraft is grounded and fixed. A failed Mars mission means a completed spacecraft, sitting in a clean room while the planets take their time, which sets up the sharpest unresolved question in planetary science right now. Since landing, Perseverance has been drilling into the floor of Jezero crater, sealing rock cores into sterile metal tubes about the size of a marker pen, and setting some of them down in a carefully mapped depot. One sample, from a rock the team named Chayava Falls, carries iron-rich mineral patterns that on Earth would usually indicate microbial chemistry. Usually. Not always. Nobody can settle that question with a rover. It requires laboratories, the kind of instruments that fill a building and cannot be flown, so the plan was to go and collect them. Mars sample return, ranked by the scientific community as the highest priority in planetary science. But the architecture never settled. NASA spent years weighing options, eventually narrowing to two: a rocket-powered sky crane landing at an estimated $6.6 to $7.7 billion, or a commercially built lander at $5.8 to $7.1 billion. A decision was expected in the second half of this year. By 2024, projected costs had climbed toward $11 billion, and that number became the weapon. Supporters argued the samples are already collected, already sitting on Mars, and may hold the first physical evidence of life beyond Earth, that abandoning them after paying to gather them would be the single strangest decision in the history of the space program. Opponents argued, with equal seriousness, that an $11 billion program would swallow the rest of planetary science whole, starving Venus missions, outer planet missions, and everything else for a decade or more. That argument split the scientific community against itself for years. In May 2025, the White House budget request called the program financially unstable and proposed ending it. In January of this year, Congress passed a spending bill that rejected most of the administration's proposed cuts, but declined to fund Mars sample return. In its place, $110 million went to a program called Mars Future Missions, funding landing technology and instruments without the goal of bringing anything home. The program office closed, the samples did not move. Meanwhile, another set of hardware is being welded together. China's Tianwen-3 entered flight hardware development this March, targeting two Long March 5 launches in late 2028, one carrying a lander and ascent vehicle, the other an orbiter, an Earth return craft. The lander will drill, scoop, and deploy a small drone to gather material from a few hundred meters around it. The goal is no less than 500 grams of Martian rock and soil, about the weight of a loaf of bread, delivered to Earth in 2031. If that schedule holds, the first Martian samples ever examined in a terrestrial laboratory will not be the ones already sitting in Jezero crater. Perseverance is not immortal. Its plutonium power source has, by current estimates, something on the order of 10 years of useful output left. Ken Farley, the mission's project scientist, put the deadline plainly. If construction of a retrieval mission does not begin within about 2 years, he does not believe it will arrive in time to be handed the tubes directly. After that, the samples remain, sealed, sterile, chemically stable, sitting in the dust of a crater that held a lake 3.5 billion years ago. They will not spoil. They will not degrade meaningfully. They will simply wait, possibly for decades, possibly for a generation of scientists who have not yet been born. And that is the shape of the inner solar system, a place where the gates open every couple of years, where the crossings take months, and where a single bad afternoon can cost half a decade. Now hold that thought, and consider what happens when the destination is not 7 months away, but years, when the gates open not every 26 months, but once in a decade, when the spacecraft must climb outward against the sun's pull for so long that the engineers who launched it retire before it arrives, because past Mars, the asteroid belt opens and the solar system stops being crowded. When Pioneer 10 crossed the asteroid belt between July 1972 and February 1973, nobody knew whether it would come out the other side. The belt looked dense on paper. Engineers genuinely feared a spacecraft would be sandblasted apart. 7 months later, Pioneer 10 emerged unmarked. The belt turned out to be one of the emptiest places we had ever flown through, a scattering of rock across a volume so vast that hitting anything requires deliberate effort. But past the belt, the emptiness stops being reassuring and starts being the whole problem. Jupiter orbits about 778 million kilometers from the Sun, 484 million miles, a little over 5 times Earth's distance. And here's what that number hides. The gap between Mars and Jupiter, on its own, is more than 3 times wider than the entire stretch from Mercury out to Mars. Everything we have spent this journey discussing, the inner planets, the launch windows, the 26-month gate, all of it fits inside a small, crowded pocket near the fire, with a canyon on the far side. Crossing that canyon means climbing, the whole way. A spacecraft heading outward is fighting the sun continuously, not dramatically, not in a way anyone would notice on a single day. The sun simply pulls and never stops, and the spacecraft slows year after year, the way a cyclist slows on a hill that never crests. Think of it as the reverse of falling. Everything gained at launch gets spent, kilometre by kilometre, buying altitude away from the sun. The upside is real. Arriving slow is easy out here. The climb does the braking for you. But the climb also takes years, and years are the one thing no engineering department has ever found a way to compress. The early crossings show exactly how the arithmetic works. Pioneer 10 launched in March 1972 and reached Jupiter in December 1973, about 21 months. Voyager 1 did it in roughly 18. Voyager 2, launched on a wider, slower arc, needed about 23. Then, in 2006, one spacecraft broke the record and has held it ever since. New Horizons left Earth faster than any object humans have ever launched. After its final solid rocket stage burned out, it was moving at roughly 58,500 kilometers per hour relative to Earth, about 36,000 miles per hour. Put that in terms your body can feel. Apollo crews took about 3 days to reach the Moon's distance. New Horizons crossed it in 9 hours. It passed the Moon's orbit before most people who watched the launch had finished their working day. 13 months later, on the 28th of February 2007, it swept past Jupiter. 13 months. Nothing has matched it. But that record contains a trap. New Horizons did not go to Jupiter. It went past Jupiter at enormous speed, and it never slowed down for anything, not for Jupiter, and not 9 years later for Pluto. The mission was built on a single hard acceptance. This spacecraft would never stop anywhere, and that is the divide that governs everything out here. Flybys are cheap, orbits are not. Arriving fast is easy. Arriving fast and staying is close to impossible, because every kilometre per second you carry into the encounter must be thrown away again by engines burning propellant you had to launch from Earth in the first place. So, which is worth more? 13 months and a few hours of data, or 6 years and a decade of it? Before answering that, one mechanism needs explaining properly, because everything that follows depends on it. A gravity assist is not a slingshot in the playground sense. Nothing pushes the spacecraft. What actually happens is a theft. Picture a tennis ball thrown gently at the front of a moving truck. In the truck driver's frame, the ball bounces off at the speed it arrived. But to someone standing on the roadside, the ball comes away far faster, because it kept its own speed and took some of the truck's. A planet works the same way. A spacecraft falls toward it, whips around and leaves on a different heading with a different speed relative to the Sun. The energy has to come from somewhere, and it comes from the planet's own orbital motion. Jupiter is genuinely slowed by every spacecraft that uses it, by an amount so small no instrument could ever measure it. A planet nearly 2 million times heavier than everything else orbiting the Sun combined, losing a whisper of momentum to a machine the size of a car. The spacecraft gains kilometers per second. Jupiter's year lengthens by an amount with dozens of zeros after the decimal point. New Horizons picked up about 14,000 kilometers per hour that way, around 9,000 miles per hour, and cut 3 years off its journey to Pluto in a single afternoon. Pioneer 11 took even more. Its Jupiter pass in December 1974 accelerated it to roughly 173,000 kilometers per hour, a speed one NASA description put at 55 times the muzzle velocity of a high-powered rifle. That encounter flung it up out of the plane of the planets and back across the entire solar system, 2.4 billion kilometers, about 1.5 billion miles, to arrive at Saturn nearly 5 years later. Free energy, paid for in time. Which brings us to the most instructive spacecraft ever sent to Jupiter and the strangest chain of consequences in the history of planetary exploration. Galileo was supposed to fly a fast, direct route boosted out of the shuttle's cargo bay by a powerful liquid hydrogen upper stage called Centaur. 2.5 years to Jupiter, roughly. Then Challenger broke apart in January 1986, and NASA re-examined everything it had been willing to fly alongside a human crew. A tank of liquid hydrogen and liquid oxygen riding in the cargo bay was no longer acceptable. Centaur was removed from the shuttle program entirely. Galileo's replacement upper stage was safer and far weaker. It could not send the spacecraft to Jupiter at all. So, mission designers rebuilt the route around gravity assists, a path they called Vega, Venus, then Earth again. Galileo finally launched on the 18th of October 1989 aboard Atlantis and reached Jupiter on the 7th of December 1995. 6 years. To a destination it should have reached in under 3. The detour was not wasted. Passing through the asteroid belt, Galileo flew by Gaspra in 1991 and Ida in 1993. And at Ida it found something nobody expected. A tiny object, barely more than a kilometre across, orbiting the asteroid. They named it Dactyl, the first moon of an asteroid ever confirmed to exist. Then, in April 1991, the mission almost ended. Galileo's main dish was designed to unfold like an umbrella, a mesh of gold-plated wire stretched over 18 ribs, 4.8 meters across, about 16 feet. Controllers sent the deploy command. 3 of the 18 ribs stayed shut. Engineers eventually traced the likely cause to something almost unbearably mundane. During the years of delay after Challenger, the antenna had been trucked across the United States and back. Pasadena to Florida, Florida to Pasadena, then Florida again. Investigators concluded that a dry lubricant bonded to the retaining pins had most likely worn away during those journeys, letting bare metal grip bare metal. NASA has been clear that the damage almost certainly existed at launch and was never caused by the long Vega cruise itself. But the launch delay is what put that antenna in the back of a truck 3 extra times. Consider what a different 1986 would have meant. Centaur survives. Galileo flies direct, arrives at Jupiter in the early 90s, and the antenna never makes those journeys. There is no way to prove the dish would have opened, but the specific wear that stopped it would not have happened the way it did. The consequences were close to fatal. That high-gain dish was designed to send data at roughly 134,000 bits per second, about 1 full image every minute. The small backup antenna, meant only for housekeeping signals, managed around 10 bits per second. Take a moment with that ratio. An image that should have taken 60 seconds would have needed more than a week. A mission built for the first number cannot be run at the second. Galileo was healthy on course, instruments working perfectly, and functionally mute. What happened next is one of the finest pieces of improvisation in the history of engineering. Teams rewrote Galileo's flight software and transmitted the new code across hundreds of millions of kilometers to a computer they could never touch again. They built aggressive data compression into a spacecraft never designed for it, so that images could be stripped down before transmission rather than after. They upgraded receiving stations on Earth and linked multiple antennas together. Goldstone in California, Canberra in Australia, the Parkes Radio Telescope, pointing several dishes at one faint signal simultaneously and combining what each of them heard. And they made brutal choices. Every observation had to justify its own bits. Most of what the mission was designed to gather was simply never taken. The final transmission rate reached about 160 bits per second at best, still a rounding error against the original design, but it recovered something in the region of 70% of the intended science. Galileo completed 34 orbits of Jupiter. It returned the evidence that Europa, Ganymede, and Callisto very probably hold liquid water oceans beneath their ice, the finding that reshaped where we look for life in this solar system. And it carried a passenger. In December 1995, Galileo released a small probe that entered Jupiter's atmosphere at roughly 170,000 kilometers per hour, survived heating that stripped away half its heat shield, opened a parachute, and transmitted for about 58 minutes as it sank into a sky with no floor. 58 minutes, barely longer than a football match. The only direct measurements of a giant planet's atmosphere anyone has ever made. Then, on the 21st of September 2003, controllers deliberately flew Galileo into Jupiter and destroyed it, not because it had failed, but because its propellant was running out, and nobody could guarantee it would never drift into Europa. A spacecraft carrying Earth microbes cannot be allowed to fall on an ocean we may one day search for life. They killed it to protect what it had found. Juno launched in August 2011, needed an Earth flyby in 2013 to gain enough speed, and slid into orbit around Jupiter on the 4th of July 2016. 5 years and roughly 2.8 billion kilometers, about 1.7 billion miles, traveled to reach a planet that sits 778 million kilometers from the Sun. And Juno did something no one had managed before. It ran on sunlight. At Jupiter, sunlight carries roughly 4% of the intensity that reaches Earth, roughly the difference between standing in open sun and standing beneath a thick, unbroken layer of winter cloud. Every outer planet mission before Juno had used nuclear power sources for that reason. Juno instead unfolded 3 enormous solar wings, each about 9 meters long, around 30 feet, the height of a 3-story house, and made it work for a decade in the harshest radiation environment in the solar system. Its final approved extension expired on the 30th of September 2025. That date coincided with a lapse in United States government funding, and NASA has not publicly confirmed the spacecraft's operating status since. The mission had also been zeroed out in the administration's budget request for the following year. Whether Juno is still listening, nobody outside the agency can currently say with confidence, which sits directly on top of an engineering disagreement that has not been settled. Juno's success made a real case. Solar panels at Jupiter are viable. They avoid an entire nuclear supply chain. They simplify launch approvals, and they cost less. Europa Clipper, now on its way, carries solar arrays too. The other camp points at the physics. Sunlight weakens with the square of distance, so at Saturn it drops to roughly 1% of Earth's, meaning arrays would have to grow to sizes that become structurally absurd. Radiation degrades solar cells steadily, dust settles on them, and a spacecraft that needs to survive in shadow or operate for decades cannot depend on a source that fades every year. Neither position is unreasonable. Solar works magnificently, right up until it does not, and the boundary sits somewhere out past Jupiter. Saturn orbits about 1.43 billion kilometers from the Sun, roughly 886 million miles, nearly 10 times Earth's distance. Pioneer 11 needed 6.5 years to get there. Voyager 1, using Jupiter's gravity, made the same crossing in about 3. Cassini took the middle path and paid for it in years. It launched on the 15th of October 1997 and reached Saturn on the 1st of July 2004. Nearly 7 years, and its route makes no visual sense at all. Venus twice, then Earth, then a long climb out to Jupiter for one more assist at the end of 2000, and only then the final fall towards Saturn. That machine went inward before it went outward. Twice. But the patience brought something extraordinary. Cassini operated for 20 years in total, 13 of them inside the Saturn system, long enough to watch seasons change on another world. And on the 14th of January 2005, it released the ESA-built Huygens probe, which parachuted through Titan's orange haze and settled onto a surface of water ice and hydrocarbon sand more than 1 billion kilometers from Earth. More than 20 years later, that remains the most distant landing human beings have ever achieved. Nothing has touched down further out since, so the trade is now fully visible. Gravity assists are not free. They are paid for in years of cruise, and those years by kilograms, instruments, fuel, science hardware that a direct launch could never have lifted. Galileo's 6-year route existed so that a weaker rocket could still deliver a full flagship payload. But every additional year adds something else. More single points of failure. More mechanisms sitting folded, unused, aging. More opportunities for one lubricant film on one set of pins to wear away in the back of a truck. And out here, nothing can ever be repaired. Not one bolt, not one wire. The entire discipline consists of building something perfectly, launching it, and then living for decades with whatever you got wrong. That poster of the solar system was never lying about the order of the planets. What it hid was the waiting. Beyond Saturn, though, even the waiting changes character, because past those rings the distances stop doubling and start multiplying, and only one spacecraft in the entire history of our species has ever gone out there and looked back at what it found. Past Saturn, the arithmetic changes character. Uranus orbits at an average of about 2.87 billion kilometers from the Sun, roughly 1.78 billion miles, 19 times Earth's distance. Neptune sits at about 4.5 billion kilometers, 2.8 billion miles, 30 times Earth's distance. But the raw numbers hide the shape of it. Look at the gaps instead. The whole journey from the Sun out to Saturn covers a certain span. The single step from Saturn to Uranus is longer than that entire journey, and the step from Uranus to Neptune is longer again. Out here, every stride is bigger than everything that came before it. The solar system stops being a sequence of destinations and becomes a place where the map keeps unrolling faster than you can walk. The light goes with it. Sunlight at Neptune carries roughly 1/900th of the intensity that falls on Earth. Stand there at local noon, under a sky the colour of deep ocean water, and you would not call it daytime. You would call it the last few minutes before full dark. And in the entire history of our species, exactly one spacecraft has ever been to either world. Every photograph humanity possesses of Uranus and Neptune from close range came from a single machine, moving fast, that could not stop and never came back. Voyager 2 passed Uranus on the 24th of January 1986. It passed Neptune on the 25th of August 1989, skimming about 5,000 kilometers above the North Pole, closer to Neptune's cloud tops than the International Space Station orbits above Earth. Then it kept going, and nothing has followed it in 4 decades. Think about what that means for a moment. Everything in every textbook about the ice giants, their winds, their tilted magnetic fields, their moons, the geysers on Triton, traces back to a few hours of observation made with cameras designed in the 1970s by a spacecraft that had already been flying for 12 years when it got there. We have better images of some exoplanets' atmospheres than we have of the 8th planet in our own solar system. That single pass only happened because of one man doing arithmetic in a summer job. In 1965, Gary Flandreau was a Caltech graduate student on temporary assignment at NASA's Jet Propulsion Laboratory. His task sounded routine: plot where the outer planets would be in the coming decades and look for useful trajectories. What he found reshaped the century. Jupiter, Saturn, Uranus, and Neptune were drifting into an arrangement that would let a single spacecraft chain them together, each one bending the path toward the next, each one donating speed. A journey that would otherwise take about 40 years could be done in under 10, but the alignment recurs only about once every 175 years. Sit with that number. The previous opportunity fell around the year 1802, when Thomas Jefferson was president and Napoleon was consolidating power in France. Nobody alive then could have used it. The next comes around the year 2152, when everyone currently breathing will be long gone. The window opened for a matter of months in the late 1970s. Flandreau found it roughly 10 years in advance, barely enough time to design, build, test and launch. Miss it, and the entire idea dies for 6 generations. Voyager 2 launched on the 20th of August, 1977, 2 weeks before Voyager 1, despite the name, because it flew the slower, wider arc that made the full tour possible. Jupiter came in July 1979, Saturn in August 1981, then 4.5 years of nothing but coasting to Uranus in January 1986, then 3.5 more years to Neptune in August 1989. 12 years from launch to the last planet. 1 rocket, 4 worlds. The alternative, 4 separate missions, 4 separate launches, 4 separate teams, would have cost far more and taken decades longer. And the machine doing it carried almost nothing we would recognize as a computer. Voyager's onboard memory totals roughly 70 kilobytes across all its systems. A single photograph taken on an ordinary phone today would be something like 50 times too large to fit inside a Voyager's entire brain. That is the whole capacity. Flight control, fault protection, science sequencing, everything. Yet during the long, quiet cruise between Saturn and Uranus, engineers on Earth rewrote that software across 1 billion kilometers of vacuum, teaching the spacecraft new image processing techniques so it could take usable pictures in light barely 1/400th of what it had at Earth. They upgraded a machine they would never touch again, using instructions that took hours to arrive. The pattern repeated in the next generation, and it repeated harder. New Horizons launched in January 2006 and reached Pluto in July 2015. 9.5 years. Most of that cruise was spent asleep. The spacecraft hibernated for long stretches, systems powered down, electronics resting, a single computer awake to send a weekly heartbeat home, specifically to slow the aging of components that could never be replaced. Then, after a decade of falling, it arrived. Closest approach put it around 12,500 kilometers from Pluto, about 7,800 miles, roughly the distance from London to Beijing, moving at close to 50,000 kilometers per hour, 31,000 miles per hour. The whole close encounter lasted hours, not days, not a season of observation. Hours. Imagine standing beside a road, once in your life, as the only vehicle you will ever see goes past at full speed. Whatever you notice in that moment is everything you will ever know, and what it noticed rewrote a world. Mountains of water ice standing kilometers high, hard as rock at those temperatures. Nitrogen glaciers flowing slowly across a plain the size of Texas. A blue layered haze in the upper atmosphere, and gas quietly escaping into space. Nobody had predicted geology that active on a body that cold and that small. Pluto should have been a frozen, dead relic. Instead, it was working. There was no second attempt. There could not be. 4.5 years later, on the 1st of January, 2019, New Horizons flew past a small, 2-lobed object called Arakoth, the most distant close encounter with anything ever performed by human beings. And then it went back to sleep. On the 7th of August, 2025, the spacecraft entered the longest hibernation of its mission, 321 days of near silence. Flight controllers at the Johns Hopkins Applied Physics Laboratory woke it on the 23rd of June this year, using commands they had uploaded 11 months earlier. Every weekly status report through that entire period came back green. New Horizons now sits about 9.5 billion kilometers from Earth, around 5.9 billion miles. A radio signal from it needs roughly 8 hours and 52 minutes to arrive. Ask that spacecraft a question over breakfast, and the answer reaches you in the small hours of the following morning. Further out still, the 2 oldest machines we have are having an argument on our behalf. Voyager 1 crossed the heliopause on the 25th of August, 2012. Voyager 2 followed on the 5th of November, 2018. The heliopause is a real, physical boundary, the point where the sun's outflowing wind of charged particles finally loses the pressure contest against the thin gas drifting between the stars. Picture a stream of water hitting a flat surface. It spreads outward in a smooth sheet until, at a certain radius, it suddenly buckles into turbulence. That ring is the boundary. The Voyagers crossed the solar system's version of it, and their instruments recorded the plasma density jumping as they passed. So did they leave the solar system? One group of scientists says clearly yes. Beyond the heliopause, a spacecraft is immersed in interstellar material rather than solar material. By the only measurable physical definition available, that is outside. Another group says no, and their reasoning is just as sound. The sun's gravity extends far beyond its wind. Out there, at distances hundreds of times further, sits the Oort cloud, an enormous shell of icy bodies still bound to the sun, still orbiting it, still part of the system by any gravitational accounting. By that definition, the Voyagers will need roughly 300 years just to reach its inner edge, and something like 30,000 years to pass out the far side. Both camps are describing the same spacecraft in the same place. They simply disagree about which boundary matters more, the one you can measure with an instrument or the one written by gravity. Nobody has settled it, and nobody needs to. The disagreement itself tells you something honest. The solar system does not have an edge. It has several, and they are nowhere near each other. Which brings us to a date that arrives in a few months. On the 18th of November, 2026, at 16 minutes past 2 in the morning Pacific time, Voyager 1 will become the first object built by human hands to sit one full light day from Earth, about 16.1 billion miles, 25.9 billion kilometers. Susie Dodd, the Voyager project manager at JPL, described what that means in the plainest possible terms. Send a command saying good morning at 8 o'clock on a Monday, and Voyager 1's answer comes back at roughly 8 o'clock on Wednesday. 49 years of continuous flight to build a 2-day conversation. But the milestone is arriving alongside something harder. Both Voyagers run on the slow decay of plutonium, and both are losing about 4 watts of electrical output every single year. 4 watts is less than a small nightlight. Lose it once and you barely notice. Lose it every year for half a century and there is almost nothing left. So the mission has become a long, careful sequence of sacrifices. The cosmic ray subsystem on Voyager 1 went dark in February 2025. On the 17th of April this year, engineers sent the command that switched off its low-energy charge particles instrument, a detector that had been measuring the structure of interstellar space since before most people watching this were born. 2 science instruments now remain operating on Voyager 1, the magnetometer and the plasma wave subsystem, and the team is attempting something audacious. They call it, internally, the Big Bang, a plan to swap out an entire group of older, power-hungry components for lower power alternatives all at once, buying enough margin to keep the spacecraft's electronics warm enough to function. They are testing it on Voyager 2 first, because it is closer to Earth and has slightly more power to spare. If it works, the same procedure goes to Voyager 1. The goal is modest and enormous at the same time. Keep at least one instrument alive on each spacecraft into the 2030s, and get both of them to their 50th anniversary in 2027. 50 years of continuous operation from a machine designed for 5. So the obvious question, when do we go back to the ice giants? The scientific community answered clearly. In the 2023 to 2032 Decadal Survey, the once-a-decade document in which planetary scientists rank what matters most, a Uranus orbiter and probe was placed at the top, the highest priority new flagship mission in the field. The original plan looked achievable. Launch in 2031 on a Falcon Heavy, take a gravity assist at Jupiter, and arrive at Uranus around 2044. 13 years of cruise. Estimated cost, roughly $4.2 billion. Then reality intervened, and it did so from an unexpected direction. Sunlight at Uranus carries about 1/400th of Earth's intensity, so solar panels are simply not an option. The spacecraft needs a nuclear power source, and NASA does not currently have enough plutonium to build one for this mission. The Department of Energy's production plans covered the missions already committed. They did not cover this one. The likely launch slipped to the mid to late 2030s, and that slip does something cruel because launch windows to Uranus are not evenly spaced. The good Jupiter alignment is what made a 13-year cruise possible. Miss it, and the trajectory has to loop more times through the inner solar system to build the same energy, stretching the crossing toward 15 years and pushing arrival into the late 2040s. A budget delay of 5 years costs closer to 10 years of science. Underneath all of that runs a disagreement that never fully resolved. A rival concept, Neptune Odyssey, would have sent a flagship orbiter to Neptune and its extraordinary moon Triton, a world that orbits backwards, almost certainly captured from the Kuiper Belt, with nitrogen geysers erupting through a surface at around minus 235 degrees Celsius, and a plausible subsurface ocean. Advocates argued that Triton offers something Uranus cannot, a captured ocean world sitting at the boundary of the known solar system, with active geology we have seen with our own instruments. The Decadal Survey chose Uranus instead, and was explicit about why. The decision turned on cost, on launch vehicle availability, and on the timing of the windows, not on a judgment that Uranus was the better science. Both sides still hold their positions. A smaller Triton-focused mission concept remains under study as a possible future candidate. Now put the whole thing in human terms. If the Uranus orbiter launches in the late 2030s and cruises for 14 or 15 years, orbit insertion falls somewhere around 2050. A child born this year would be in their mid-20s before that spacecraft leaves the ground, and closer to 40 when it arrives. The scientists who fight for this mission today will mostly be retired. Some will not be alive. The people who received the first close images of Uranus in living memory have not yet applied to university. That is not a failure of ambition. Every element of it, the plutonium, the alignments, the 15-year cruise, comes from the same source, a solar system that is not far away exactly, but slow in a way that outlasts human careers. And that raises a question we have not yet faced directly, because reaching these places is only half the problem. 2 spacecraft launched in 1977 are still transmitting, and the reason has almost nothing to do with trajectory design. It has to do with whether anything we build can survive out there at all. Decades of radiation, of cold, of mechanisms that must work once, perfectly, after 20 years of never being used. We have learned how to get there. Staying alive when you arrive turns out to be far harder. Everything discussed so far has been about arithmetic, trajectories, windows, velocity, patience. All of it assumes the spacecraft is still working when it gets there. Often, that is the harder assumption. A machine sent to the outer solar system must function, without maintenance, for longer than most marriages last. It must sit unused for a decade, and then perform a maneuver perfectly on the first attempt. It must survive an environment that is quietly, continuously trying to take it apart. And before any of that, it needs electricity. Past Jupiter, sunlight thins out too far for solar panels to carry most mission profiles. So spacecraft carry something else, a device with a name far more intimidating than the object itself. A radioisotope thermoelectric generator has no engine, no fuel line, no valve, and no moving parts of any kind. Inside sits a lump of plutonium-238, an isotope that does one thing. It decays, and decay releases heat. Wrap that hot core in materials whose outer surface stays cold, and you create a temperature difference between 2 points. Certain materials turn a temperature difference directly into electric current. The same principle behind the thermocouple in a gas boiler, which senses a pilot flame by producing a tiny voltage from heat alone. Scale that up, keep one side hot for decades, and you have power with nothing to break. The generator flown on Perseverance holds about 4.8 kilograms of plutonium dioxide, roughly 10.5 pounds, about the weight of a large house cat. That fuel produces around 2,000 watts of heat and converts about 110 watts of it into electricity. 110 watts, slightly more than 2 old-fashioned incandescent light bulbs. That is the entire electrical budget of a machine exploring another planet. The conversion is brutally inefficient. Well over 90% of the heat simply radiates away, but nothing wears out. No pump, no bearing, just physics winding slowly down. Plutonium-238 has a half-life of 87.7 years, meaning that after that span, exactly half of it remains. Not roughly half, half, which produces something strange and slightly haunting. The power curve of a spacecraft can be calculated before it ever leaves the pad. Engineers know, decades in advance, almost precisely how much electricity a machine will have in its 30th year, its 40th, its 50th. Think about what that means for the people who build these things. A car might last 20 years or 5, depending on how you treat it. A deep space power source has no such uncertainty. On the day it is sealed, the decline has already been written, and every engineer on the project can read it. They know when the lights go out. They have always known, which leads to something almost nobody outside the field thinks about. The United States stopped producing plutonium-238 in the late 1980s. For roughly 2 decades afterward, NASA's deep space program ran partly on plutonium purchased from Russia. Domestic production restarted in 2013 at Oak Ridge National Laboratory in Tennessee. The early output was almost symbolic, around 50 grams a year. Automating a key step in the process pushed that toward 400 grams. The Department of Energy set a target of an average of 1.5 kilograms per year by 2026, and in 2023 shipped 0.5 kilogram in a single delivery, the largest since the restart. Now hold that number against the hardware. A single generator needs about 4.8 kilograms of fuel. At the target production rate, the entire United States requires roughly 3 years to make enough plutonium for one power source. To stretch what exists, DOE and NASA blend older, decayed plutonium with newly made material at about 2 parts old to 1 part new. At the planned rate, NASA can fly a nuclear-powered mission roughly once every 4 years. Not once a year, once every 4. So is that enough? NASA officials have stated publicly that the Department of Energy can meet the agency's current commitments. The mission's already approved, with their launch dates already set. The production ramp is real. The shipments are getting larger. Officials have described the capability as re-established rather than experimental. But the same officials have acknowledged something else. Those production plans do not include the Uranus orbiter and probe, the highest-ranked flagship mission in planetary science. One camp argues the system is working, capacity is climbing, blending stretches the inventory, and every committed mission will fly with the power it needs. The other camp points out that the field's own top priority sits outside the plan, that the ramp has consistently taken longer than promised, and that a supply chain producing a few hundred grams a year cannot support ambition measured in flagships. Neither side is being unreasonable. They are looking at the same numbers and drawing different conclusions about what counts as enough. But notice what has happened here. For most of the space age, the limits on exploring the outer solar system were physics and money. Today, the binding constraint on reaching Uranus is the annual output of one radioactive isotope from one laboratory in Tennessee. Not orbital mechanics, not engineering, chemistry, and how much of it we choose to make. Power is only the beginning, because the environment itself is hostile in ways that are easy to overlook. Space is filled with charged particles moving at enormous speed. Every one that passes through a microchip can flip a bit, turn a stored one into a zero, and over years that bombardment physically damages the silicon. Circuits that worked perfectly on Earth slowly accumulate scars nobody can see. Temperature does its own work. A spacecraft passing in and out of shadow swings through hundreds of degrees over and over. Every cycle expands and contracts the metal and the seals, and materials that flex thousands of times eventually grow brittle. the same fatigue that snaps a paperclip you have bent back and forth once too often. Lubricants behave badly in vacuum. Some freeze solid. Some slowly evaporate, because in the absence of atmospheric pressure, oils simply boil away over years. Some creep out of the joints they were meant to protect and migrate somewhere useless. Dust settles on solar arrays and never washes off. Batteries lose capacity permanently with every charge cycle, exactly as a phone battery does after 3 years, except no one can replace it. And here is the part that governs all of it. Nothing out there can ever be repaired. Not a bolt, not a wire, not a stuck mechanism. The only defense is redundancy, carrying 2 of everything critical, sometimes 3. Redundancy always runs out. It only ever buys time. Spirit landed on Mars in January 2004, built for 90 Martian days and a drive of 600 meters, about the length of 6 football pitches. It ran for more than 6 years and covered 7.7 kilometers, roughly 4.8 miles, mostly because Martian winds kept randomly cleaning the dust off its solar panels. Nobody designed that. The planet simply did it, over and over, and gave the mission years nobody had budgeted for. Then, in 2009, Spirit drove into a patch of soft soil and sank. Its wheels turned and found nothing to grip. That would have been survivable, except for one thing. Mars winters are brutal, and at Spirit's latitude the sun sits low. The rovers survived winter by parking on a slope, deliberately angling their solar panels toward that low sunlight, the way you tilt a book to catch the light from a window. Trapped on flat ground, Spirit could not achieve the angle. Picture what followed. Each day the sun climbs a little lower. The panels take in a little less. The batteries deliver a little less charge overnight, and the heaters that keep the electronics from freezing draw a little more. There is no dramatic failure, only a machine getting colder and quieter and slower, in a place where the night reaches minus 100 degrees Celsius. Spirit's last transmission reached Earth on the 22nd of March, 2010. Engineers kept calling for more than a year. In May 2011, they stopped. It is still sitting exactly where it stopped. Its twin, Opportunity, landed 3 weeks later on the other side of the planet, built to the same 90-day specification. It operated for 14.5 years and drove 45 kilometers, 28 miles, further than any vehicle has ever traveled on another world, and further than a marathon, 57 times its design lifetime. Then, in June 2018, a dust storm rose and kept rising until it encircled the entire planet. Sunlight at the surface collapsed. Opportunity's last transmission reached Earth on the 10th of June, a reading of falling power and darkening sky. NASA sent more than 1,000 recovery commands over the following 8 months, waiting for the seasonal winds that had rescued the rovers so many times before. Nothing came back. In February 2019, the agency stopped calling. 2 machines, identical, both built for 90 days. One killed by soft soil, one killed by weather, neither by anything an engineer could have fixed. Cassini's ending was different and harder because nothing had gone wrong. Designed for roughly 11 years, it operated for 20, nearly 13 of them inside the Saturn system. By 2017, the spacecraft was still healthy, still returning science, still answering every command. But it was running out of propellant, and propellant is what maintains control. Without it, Saturn's gravity and Titan's gravity would keep reshaping Cassini's orbit indefinitely, and nobody could guarantee where a dead spacecraft would eventually end up. Cassini had not been sterilized to the standard required for contact with a habitable world, because when it launched in 1997, nobody knew Enceladus had an ocean. Cassini had found that ocean itself, so the team spent roughly a decade deliberating, and then did the only thing that removed all risk. Starting in April 2017, they flew 22 orbits threading the 2,000-kilometer gap between Saturn and its rings, a region no spacecraft had ever entered, and on the 15th of September, they aimed it into the planet. Cassini transmitted the whole way down, its small thrusters fighting the thickening atmosphere to hold the antenna toward Earth, sending back the first direct measurements of Saturn's atmospheric composition until the structure broke apart. The signal took 83 minutes to cross the distance. By the time the telemetry flatlined in the control room, the spacecraft had been gone for nearly an hour and a half. The people who destroyed Cassini were the people who had spent their careers building and flying it. Some had been on the project since the 1980s. The requirement that killed both Cassini and, earlier, Galileo has a name: planetary protection, and it remains genuinely contested. The case for it is strong and widely held. Introducing terrestrial microbes into a subsurface ocean would be irreversible, not undoable, ever. Worse, contamination would poison the very question we came to answer, because any biological signal found afterward would be permanently ambiguous. Nobody would ever know whether we had discovered life or merely found our own. The case against is narrower, but seriously argued. Some researchers contend that current sterilization standards are calibrated far above the real risk, that Earth microbes are extraordinarily unlikely to survive years of hard radiation, vacuum, and deep cold, then penetrate kilometers of ice, then thrive in an alien chemistry. On that reading, compliance costs hundreds of millions of dollars per mission, drives up complexity, and forces the destruction of functioning hardware for a hazard that may be close to negligible. The institutional consensus sits firmly with caution, and the reasoning behind it is sound. But calling the debate settled would be dishonest. It is not. Which brings us to a spacecraft currently in flight. Europa Clipper launched in October 2024 and arrives at Jupiter in 2030. It will make 49 flybys of Europa rather than orbiting it, and its death is already scheduled. The current mission plan ends with a deliberate impact into Ganymede on the 3rd of September 2034, 45 days after the final Europa flyby. Ganymede was chosen precisely because it is safer to hit. Its ice shell is substantially thicker than Europa's, and its surface is probably not geologically active today, so contact between spacecraft debris and any ocean below is far less likely. Consider what that means as a human document. Engineers who spent a decade building that machine wrote the date of its destruction into the plan before it left the ground, down to the day and the latitude and the local solar time of the impact. Every spacecraft in this story, past and present, depends on one piece of ground infrastructure: NASA's Deep Space Network. 3 antenna complexes, spaced roughly evenly around the globe: Goldstone in California, Madrid in Spain, and Canberra in Australia, so that as Earth turns, at least one is always facing any given spacecraft. 3 sites, somewhere near 60 missions. In July 2023, NASA's Office of Inspector General published an audit with an uncomfortable conclusion. The network was oversubscribed, with demand exceeding supply by as much as 40% at peak times. Missions were already unable to fully meet their science objectives because they could not get antenna time. The audit projected excess demand reaching about 50% by the 2030s, and found the upgrade program meant to fix it running behind schedule and over budget. And the hardware is aging. In September 2025, the 70-meter dish at Goldstone, a 230-foot antenna, one of only 3 of that size on Earth, went offline after an over-rotation accident, and the largest antennas are precisely the ones needed for the faintest, most distant signals. The implication is quiet and cumulative. More missions competing for the same 3 sites means less data from each one, not a dramatic loss, a slow thinning of everything we learn. So here is where all of it lands. We build machines to outlast careers. Spirit and Opportunity were designed for 90 days, and one of them ran 57 times longer. Cassini was designed for 11 years, and gave 20. The Voyagers were designed for 5 and are approaching 50. They are, by a wide margin, the most durable objects our species has ever made. And having built them to survive almost anything, we then find ourselves in rooms deciding how they should die, steering healthy spacecraft into planets, writing impact coordinates years in advance, calling a rover for 8 months after we know it will not answer. That is not a failure. That is what it looks like to take the possibility of alien life seriously enough to sacrifice for it. But notice what every one of these machines has in common. None of them needed food. None of them needed air or sleep or company. None of them aged in any way that mattered, or grew frightened, or wondered whether the people who sent them were still waiting. Every calculation in this story so far, every trajectory, every hibernation, every decade of patient cruise has assumed a passenger made of metal. Put a human being inside, and almost none of it survives contact with biology. A spacecraft can sleep for 9 years and wake up without a word of protest. New Horizons did exactly that. Powered down, drifting, then rousing on a stored command and reporting itself in perfect health. Try that with a person. A human being is not a payload. A human being is a continuously running chemical process that must be fed, watered, breathed, cooled, warmed, cleaned, and shielded. And every single one of those needs arrives as mass. Food has weight. Water has weight. The oxygen has weight. And so does the machinery that scrubs carbon dioxide back out of the air. Waste processing has weight. So does the radiator that dumps body heat, and the shielding, and the redundant copies of all of it, because a failed air system on Earth is an inconvenience, and a failed air system at Mars is a funeral. Then the tyranny compounds. Mass demands propellant. Propellant demands a larger vehicle. A larger vehicle demands more launches, and more launches demand budgets that must survive multiple political administrations. A robot costs kilograms, a crew costs tons, but that is only the accounting. The harder problem is what happens inside the body. The cheapest way to send people to Mars and bring them home runs roughly 900 days, door to door, about 180 days outbound, around 500 days on the surface, because the return window does not open sooner. Then another 180 days home, 2.5 years. A child who started school the week the crew launched would be finishing their 2nd full year of lessons by the time they came back. And that number is not negotiable by willpower or funding. The 500 days on the surface are dictated purely by where the 2 planets happen to be. Now hold that against what human beings have actually done. The longest continuous spaceflight in history belongs to Valery Polyakov, a Russian physician who trained in space medicine and then volunteered to use his own body as the experiment. He launched on the 8th of January 1994 and returned on the 22nd of March 1995. 437 days aboard the Mir space station, 14.5 months, a little over 7,000 orbits of Earth. He chose that duration deliberately. Polyakov wanted to demonstrate that a human being could survive, physically and mentally, for as long as a round trip to Mars would demand. He exercised strenuously for 2 hours every day for the entire flight. When the capsule landed on the Kazakh steppe, returning crews were normally lifted out and lowered into a reclining chair, because a body that has spent a year without gravity struggles to hold itself upright. Polyakov refused. He walked the short distance to the chair himself. He also came back several centimeters taller than he left, because 14 months without a planet pulling on him had let the discs in his spine expand. That record has stood for more than 30 years. Nobody has broken it. And 437 days is not even half of 900. The body reads weightlessness as a message. You no longer need this. Bone is the clearest example. Without countermeasures, astronauts lose somewhere around 1 to 1.5% of bone mineral density per month in the weight-bearing parts of the skeleton, the hips, the spine, the legs. Put that beside ordinary human aging. An older adult on Earth losing bone density might lose roughly 1% in a year. In orbit, that same loss arrives every month, sometimes faster. Muscle follows. Calves and back muscles waste even with hours of daily resistance training, And imaging of returning crews shows particular shrinkage in the deep muscles that stabilize the spine, the ones you never think about until they stop working. The heart deconditions too, because pumping blood upward against gravity is a workout it no longer has to do. And the fluids move. On Earth, gravity keeps roughly a couple of litres of body fluid pooled in your lower half. Remove gravity and it migrates toward the head. Puffy face, thin legs, permanent mild congestion, like the first day of a heavy cold that never quite clears. That fluid shift causes something nobody anticipated when human spaceflight began. Raised pressure inside the skull appears to push on the back of the eyeball. The rear surface flattens slightly. The optic nerve swells. Vision changes measurably, and in some astronauts, those changes persist long after they come home. The condition now has a name: spaceflight-associated neuroocular syndrome. Researchers still do not fully understand the mechanism, and no reliable countermeasure exists. Think about that for a moment. Not radiation, not bone loss, simply the fact that fluid in a human body does not know where down is anymore, and the eye pays for it. Then came the twin study, and it went deeper still. When Scott Kelly spent 340 days aboard the International Space Station, NASA had something researchers almost never get: a genetically identical control subject. His twin brother Mark stayed on Earth. The comparison found changes across nearly every system they measured. Gene expression shifted, thousands of genes turning up or down. Most of that reverted within 6 months of landing, but a small fraction had not returned to baseline. Telomeres, the protective caps on the ends of chromosomes, lengthened unexpectedly during the flight, and then shortened rapidly after return. Some cognitive test scores declined in the months following landing. 1 year. In low Earth orbit, still inside the protection of Earth's magnetic field. A Mars crew would be gone for nearly 3, with none of that protection at all. Which brings us to the constraint that nobody has solved, and possibly nobody can. Earth sits inside a magnetic field generated by molten iron churning in its core. That field deflects most of the charged particles streaming through space, funneling them toward the poles where they become auroras. It is, in a very literal sense, a shield we live inside without noticing. Step outside it, and the shield is simply gone. Deep space carries 2 threats: solar particle events, sudden bursts from the sun that can deliver a dangerous dose in hours, and galactic cosmic rays, atomic nuclei accelerated to nearly light speed by supernova elsewhere in the galaxy, arriving constantly from every direction, so energetic that ordinary spacecraft walls barely slow them. We have measured this precisely because Curiosity carried a radiation detector on its way to Mars. Inside the spacecraft, during cruise, the instrument recorded an average of about 1.8 millisieverts per day. Here is what makes that number land. A person living on Earth receives roughly 2 to 3 millisieverts from natural background radiation in an entire year. A single day in deep space delivers most of a year on the ground. Run the full model, 180 days out, 500 on the surface, 180 back, and the total comes to roughly 1 sievert. Based on long-term population studies, a dose of 1 sievert is associated with about a 5% increase in lifetime risk of dying from cancer. 5%. Not a certainty, not nothing. And here the science becomes genuinely unsettled, not about the physics, but about what we should permit. In June 2021, the National Academies of Sciences, Engineering and Medicine published a report at NASA's own request, chaired by the radiologist Hedvig Hrikak. The committee recommended NASA adopt a single career-long limit of about 600 millisieverts, applied to every astronaut regardless of age or sex, a figure derived from the risk to a 35-year-old woman, the group considered most vulnerable to radiation-induced cancer. That recommendation was designed to make mission assignment fairer. Under the older approach, the acceptable dose varied by age and sex, which quietly favoured older male astronauts. But the same report noted something uncomfortable. NASA's own published analyses show that any realistic Mars crew will exceed 600 millisieverts, which means every such astronaut would fly on a formal waiver, a signed acknowledgement that the agency is knowingly exceeding its own health standard, and the agencies do not even agree on the shape of the question. ESA sets a career limit of 1 sievert, a dose. NASA's framework has historically asked something different. How much extra chance of dying from cancer is acceptable, capped at 3%? One is a ceiling on exposure. The other is a ceiling on probability. They are not translatable into each other in any clean way. Critics of the waiver approach have put it bluntly. A 35-year-old woman flying right at that limit could face a substantially elevated chance of dying within 15 to 20 years, and calling that acceptable through paperwork troubles them deeply. Defenders answer that astronauts have always accepted extraordinary risk knowingly, that the alternative is never going, and that transparent individual risk communication is the honest solution rather than a blanket prohibition. Neither side is careless. Both are trying to protect the same people. Underneath all of it sits a gap in the evidence that should make everyone uneasy. Cancer risk from radiation is reasonably well characterized because we have decades of population data from Earth. Effects on the central nervous system are not. Animal studies exposing rodents to simulated cosmic rays have found changes in cognition and behavior. Whether those results translate to humans at realistic doses over realistic timescales remains genuinely unknown. No human being has ever spent 2 years outside Earth's magnetic field, so no data set exists. We are not choosing between a known risk and a known safety. We are choosing while holding a number nobody can yet write down. The obvious objection is shielding. Add mass, block the particles. Engineers have studied every serious option. Water works well and doubles as drinking supply, but water is heavy and every kilogram must be launched. Polyethylene performs better per kilogram than aluminium because it is rich in hydrogen, and hydrogen is unusually effective at absorbing these particles. Active magnetic shields, generating an artificial magnetosphere around the ship, remain concepts on paper with enormous power and mass demands. But galactic cosmic rays introduce a cruel complication. When an extremely energetic nucleus slams into a metal hull, it does not simply stop. It shatters the atoms it hits, producing a spray of secondary particles that continue onward. Thin or moderate shielding can therefore, in some circumstances, deliver a worse dose than no shielding at all, the wall becoming a source. Getting real protection means enough material to absorb the entire shower, which means a great deal of mass, which means propellant, which means the whole tyranny begins again, and one countermeasure that would help enormously has never been attempted. Spinning a spacecraft would press its occupants outward against the hull, producing something the body reads as gravity, the same force that holds water in a bucket swung on a rope. The physics is elementary. The engineering is not, and the biology is entirely untested. No spacecraft has ever flown artificial gravity at crew scale, not once. At small rotation radii, spinning fast enough to produce useful force introduces disorienting effects in the inner ear. Turn your head and the world seems to tumble. Larger structures spin more gently, but require building something enormous in orbit. So the single most promising defense against bone loss, muscle wasting, cardiovascular decline, and probably the eye syndrome as well remains, after 70 years of spaceflight, a thing we have never once tried, which leaves the part that receives the least money and may prove the least solvable. Between June 2010 and November 2011, 6 volunteers sealed themselves inside a windowless facility in Moscow for 520 days. Mars 500, a full-duration simulated mission with realistic communication delays, no natural daylight, and no way out. Researchers led by Matthias Basner track them with wrist monitors, recording more than 4 million minutes of movement and light exposure, plus weekly tests of alertness and performance. What the data showed was quiet and steady and slightly chilling. The crew moved less as the mission progressed. Not dramatically, systematically. Quarter by quarter, active waking movement declined while sleep and rest time increased. Researchers called it hypokinesis. Some describe the pattern as a kind of behavioral torpor. Light exposure dropped throughout. Most crew members developed at least one of the following: disturbed sleep quality, measurable lapses in vigilance, or a sleep-wake cycle drifting out of alignment with the clock they were meant to keep. They were not in danger. They were not in space. They knew a door existed. And still, over 17 months, 6 healthy screened volunteers slowly wound down. Separate analyses of the same crew found a pattern researchers have named the third quarter phenomenon. Morale dipping, not at the start and not at the end, but somewhere past the midpoint, when the novelty has fully worn off and the finish is still impossibly far away. Anyone who has endured a long illness or a long deployment, or simply a hard winter, knows the exact shape of that curve. Beyond Mars, the isolation stops being psychological and becomes physical law. At Jupiter's distance, a radio signal takes roughly 35 to 50 minutes to cross one way, depending on where the planets sit. A question asked and answered spans well over an hour. Conversation, in any sense you would recognize, becomes impossible. You cannot interrupt. You cannot be comforted in real time. You send messages into a gap and receive messages from a past that has already moved on. Now place yourself inside that. Imagine a crew member develops severe abdominal pain 9 months out. Nobody is coming. No evacuation exists. No hospital. No second opinion arriving in time to matter. You can describe the symptoms and wait most of an hour for a specialist on Earth to respond, by which point the situation has already changed. Whatever happens next, the crew solves alone, with whatever they packed. That is not a training deficiency. That is the speed of light. One idea keeps surfacing as a way around all of this. Put the crew to sleep. Induce torpor, deliberately lowering metabolism and body temperature so that a person needs less food, less oxygen, less space, and perhaps suffers less psychologically. ESA and others have funded serious studies. Medicine already uses controlled cooling in some surgical and cardiac arrest settings for hours. But months of induced torpor in a healthy human being has never been done. Not once. The physiology of long-term hibernation in mammals that do it naturally is still not fully understood, and humans are not among them. The concept is legitimate research. It is not a solution, and honesty requires saying so. So the picture assembles, and it is not the one most people expect. If someone handed us a propulsion system tomorrow that could carry a crew to Jupiter in 18 months, we still could not go. Not because of the rocket, because we do not know what 4 years of cosmic rays does to a human brain, because we have never flown artificial gravity, because 6 volunteers in Moscow slowly stop moving, because the eye changes and we cannot yet explain them. Robots reached Jupiter in 1973. More than half a century later, human biology is the wall, and the deepest problem is not even medical, it is ethical. Informed consent means a person understands the risk they are accepting, but when the central nervous system effects are unquantified and the agencies disagree structurally about how to measure danger, and the waiver system exists precisely because the standard cannot be met, what exactly is being consented to? You can sign a form. Signing does not make the number knowable. That is the honest position, and there is something almost dignified in it. We are not being reckless. We are refusing to send people until we understand what we would be doing to them, which is, by any reasonable measure, exactly the right instinct. But it leaves one question standing, and it is the question everyone eventually asks. If biology sets the limit, and the limit is time itself, could we simply build something fast enough to make the journey short? The honest answer is, partly. Not nearly as much as people hope, and not in the way most people imagine, because the first limit is not engineering ambition, it is chemistry. A chemical rocket works by burning fuel and throwing the hot gas out of a nozzle. How fast that gas leaves determines everything, and the speed is set by how much energy chemical bonds can release when they break. The very best chemical combinations we know, hydrogen and oxygen, produce exhaust leaving at roughly 4.5 kilometers per second, around 16,000 kilometers per hour, or 10,000 miles per hour. That number is not a manufacturing limitation. It is close to the ceiling that chemistry itself permits. Engineers have spent 70 years refining these engines, and the gains now come in fractions of a percent. We are essentially finished. Whatever comes next has to work on a different principle entirely. The most obvious alternative has existed on paper and on test stands for more than 60 years. A nuclear thermal rocket replaces combustion with a reactor. Hydrogen flows through the hot core, absorbs enormous heat, and blasts out of the nozzle far faster than any chemical reaction could push it. No burning, just a nuclear furnace and a working fluid. By DARPA's own assessment, the approach offers something like 2 to 5 times the efficiency of chemical propulsion in space. And we built them. Under Project Nerva, through the 1960s and into the early 70s, engineers ground-tested a series of nuclear rocket engines in the Nevada desert. They ran. They produced thrust. They were, by the standards of the era, close to flight-ready when the program was cancelled. Half a century later, the idea came back. DARPA and NASA announced a partnership in January 2023 to fly a nuclear thermal engine in space, a demonstration called Draco, with Lockheed Martin and BWX Technologies building the hardware. In 2025, it ended. Rob McHenry, DARPA's deputy director, explained the reasoning afterward. The program had been conceived on 2 assumptions: that launch was expensive and that nuclear thermal was the right answer for certain missions. Then came what he called a precipitous decrease in launch costs, driven largely by reusable rockets. Over the life of the project, he said, both assumptions weakened. NASA's budget request for the following year went further, removing funding not only from nuclear thermal, but from nuclear electric propulsion as well. The agency's own language was blunt. These are costly investments. They would take many years to develop, and they have not been identified as the propulsion mode for deep space missions. But the argument did not end there, and this is where it becomes genuinely unsettled. A number of officials and engineers now argue the opposite of the original plan. Not that nuclear propulsion is wrong, but that nuclear electric propulsion is the better long-term architecture. A reactor generating electricity to run high-efficiency thrusters continuously, rather than a nuclear furnace producing brief violent bursts. Less thrust, far more total velocity change, and no need to store liquid hydrogen for years. Others counter that nuclear electric systems are heavier, more complex, and further from flight than nuclear thermal ever was, and that cancelling a nearly built demonstration to chase a less mature concept is how technology programs die permanently. Both camps want the same thing. Neither has won. Meanwhile, one alternative has been quietly flying for decades, and almost nobody outside the field notices it. Ion propulsion uses electricity to strip electrons from a gas, usually xenon, and then hurls the resulting charged atoms out through electric fields at speeds no chemical reaction could ever produce. The catch is thrust. Dawn's ion engines produced roughly the force of a single sheet of paper resting on your open palm. That sounds useless. It is not, and understanding why unlocks the whole logic of deep space. A chemical engine gives you everything in minutes and then stops forever. An ion engine gives you almost nothing and never stops. Run that whisper of force for years, in a vacuum with nothing to resist it, and the velocity accumulates relentlessly. You trade acceleration for total change in speed, and total change in speed is the only currency that matters out here. Deep Space One proved it in 1998. Hayabusa 2 used it to reach an asteroid and come home. Bepi Colombo's transfer module runs on it right now. And Dawn did something with it that no chemical spacecraft could have afforded. It travelled to the asteroid Vesta, entered orbit, spent 14 months studying it, then left orbit entirely and flew onto the dwarf planet Ceres and entered orbit there too. The first spacecraft in history to orbit two separate worlds beyond Earth. Not because it was fast, because it never stopped pushing. Another approach dispenses with propellant altogether. Light carries momentum. When photons strike a mirrored surface, they deliver a real, measurable push, vanishingly small, but continuous and free. Make the mirror large enough and thin enough, and sunlight becomes a wind. This is not theory. JAXA flew Icaros in 2010, the first spacecraft to sail between planets on sunlight alone. The Planetary Society's crowd-funded LightSail 2 demonstrated controlled solar sailing in Earth orbit from 2019. NASA's Advanced Composite Solar Sail System unfurled a new generation of sail booms in 2024. The technology works, but sunlight obeys the same law as everything else out here. Intensity falls with the square of distance. A sail that pushes usefully near Earth becomes nearly worthless past Jupiter, exactly where you most need help. Laser-driven concepts try to solve this by replacing the Sun with enormous ground-based arrays, Breakthrough Starshot being the best known. The physics is sound. The engineering, honestly, is nowhere close. And then there is the road we deliberately did not take. Project Orion proposed detonating small nuclear devices behind a heavily armoured pusher plate, riding the shock waves. The performance figures were extraordinary, genuinely capable of crewed missions to the outer planets on timescales measured in years, not decades. The physics was never the problem. Fallout was, and so was the 1963 treaty banning nuclear detonations in space. The program ended, and nothing has replaced it. Fusion and antimatter sit in a different category again, permitted by physics and practically unavailable. We cannot yet sustain fusion for power on the ground, and the entire quantity of antimatter humanity has ever produced would not boil a kettle, which leaves one idea that receives almost no public attention and might matter more than all of them. Think about where the propellant actually goes on an outer planet mission. An enormous fraction of it exists for one purpose: slowing down at the far end. Orbit insertion, the burn that turns a flyby into a stay. Aerocapture removes that burn entirely. A spacecraft arrives, dips once into the target planet's upper atmosphere, sheds its excess speed as heat behind a shield, and emerges captured into orbit, having spent almost no propellant at all. One pass. The same principle as a swimmer's hand dragging through water to slow a turn, except the water is a planet's atmosphere, and the turn is measured in kilometers per second. The consequences cascade beautifully. No insertion propellant means a far lighter spacecraft. A lighter spacecraft can launch onto a faster trajectory. A faster trajectory means a shorter cruise, potentially years shorter for an ice giant mission. Engineers have studied aerocapture seriously since the 1980s. It has never been flown, not once, on any planetary mission. Assessments have generally concluded that the technique is ready for Venus, Mars, and Titan, where the atmospheres are relatively well characterized. The ice giants are harder, their upper atmospheres are poorly measured, and a spacecraft that dips too deep burns up, while one that dips too shallow flies away forever. Decadal surveys have repeatedly asked for risk reduction work before a multi-billion-dollar flagship stakes its entire existence on a maneuver nobody has ever performed. That is a reasonable position. So is the counter-argument that the technique will never be proven until somebody flies it, and that every year of delay costs years of crews on missions we have already decided we want. Add all of it together: the ion engines, the sails, the aerocapture, the nuclear systems if they are ever revived, and the realistic gain is roughly a factor of 2, not 10, not 100. 2. A 15-year cruise might become 8. A 7-month Mars crossing might become 4 or 5. Meaningful, genuinely valuable, but nothing that turns the solar system into a place you can visit within a normal working life. And while we debate it, the queue keeps lengthening. Europa Clipper left Earth in October 2024 and arrives at Jupiter in 2030 after crossing about 2.9 billion kilometers, 1.8 billion miles. It will not orbit Europa. Jupiter's radiation would destroy the electronics within months. Instead, it will orbit Jupiter and make 49 separate flybys of Europa, ducking in and retreating out again, spending most of its time outside the worst of the radiation belts. And its central hope just got harder. In May of this year, a team led by Lorenz Roth at KTH in Sweden, working with Kurt Rutherford at the Southwest Research Institute, published a reanalysis of 14 years of Hubble observations of Europa. The original claim from 2012 and 2014 had reported ultraviolet signatures consistent with water vapor plumes erupting from the Moon's subsurface ocean at 99.9% confidence. The reanalysis dropped that confidence to below 90%. The cause was mundane and slightly terrifying. If Europa's position within a Hubble image was off by even a pixel or two, the interpretation changed. Add unmodelled hydrogen from the Moon's thin atmosphere, and what looked like a plume might simply have been noise. Notice who published this. Rutherford co-authored the original detection. He then spent years re-examining his own most famous result and reported publicly that it was weaker than he had believed. That is what scientific integrity actually looks like, and it costs something. The plumes are not ruled out. Clipper will look for them directly, with far better instruments than Hubble could bring to bear. But if they are absent, then sampling Europa's ocean means drilling through kilometers of ice, a mission nobody has designed, funded, or plausibly scheduled before the middle of the century. Dragonfly launches in July 2028 on a 6.5-year cruise, arriving at Titan in December 2034. A nuclear-powered rotorcraft the size of a car, flying between dunes on a moon where the air is 4 times thicker than ours and gravity is 1/7 as strong. Total cost, $3.35 billion. The Enceladus Orbilander, ranked second among new flagship priorities, exists as a concept targeting an October 2038 launch, with its science campaign running in the early 2050s. ESA's JUICE launched in April 2023 and arrives at Jupiter in July 2031. 8 years. Now sit with the arithmetic of that. An engineer joining the Orbilander team as a graduate would be approaching retirement when the first landed measurements arrive. The people who will actually operate that spacecraft, read its data, and publish what it finds are, in many cases, still in school. Some have not been born. Missions now being designed will return their answers to people not yet hired. And here is the connection almost nobody makes. Duration is not just a scientific inconvenience. Duration is the budget. A spacecraft in cruise still needs a flight team. Navigators, thermal engineers, software specialists, mission planners, all working, all paid, every year for a spacecraft that is doing nothing but falling. Add antenna time on the ground network. Add facilities. Add the reviews, the contract management, the archives. Cassini's total program cost roughly $3 to $4 billion across 2 decades, and a great deal of that was simply the price of existing for 20 years, which produces the argument that has fractured planetary science repeatedly. Every flagship absorbs an enormous share of a fixed budget for a very long time, and while it does, smaller missions do not launch. That tension surfaced around Mars sample return, and it surfaced again as Dragonfly's costs grew. One camp argues flagships are the only way to answer the biggest questions. The other argues that a decade of medium missions returns more total science than a single enormous one. Nobody has resolved it, because both are demonstrably true. But something else has kept all of this alive, and it is not propulsion. Voyager is now commanded by engineers who were born after it launched. People who inherited a spacecraft the way you inherit a house, learning its quirks from those who came before, writing procedures for a machine older than they are. Cassini's team included individuals who spent an entire professional life on one spacecraft. They joined in their 20s in the 1980s and stood in a control room in 2017 watching the telemetry go flat. That continuity, institutions like JPL and the Applied Physics Laboratory, holding knowledge across generations, training successors, keeping a mission alive through decades of shifting budgets and administrations, is the real enabling technology of deep space, not the engines, the handing over. And when it ends, ordinary people feel it. When opportunity fell silent in that dust storm, the grief was not confined to engineers. People who had never worked in spaceflight, who could not have named a single instrument on the rover, wrote about it, mourned it, felt something close to bereavement for a machine on another planet. That reaction says something important. These missions are slow enough that we grow attached to them, long enough that they become part of the furniture of a life, which brings us back to that picture on the classroom wall. The spacing on that page was never physics, but the deeper problem was that it was measuring the wrong thing entirely. It was drawn in kilometers, and kilometers were never the currency. It was a distance map for a place where distance does not set the price. So, draw the honest version. On that poster, the gap between worlds would not be measured in millions of kilometers. It would be measured in years of human life. Mars sits 7 months away. Jupiter, 5 years. Saturn, 7. Titan, 6.5. Uranus, 15. And counting, because nobody has started building it. Enceladus, 12 years of flight after a launch that has not been funded, delivering its answers to a generation currently learning to read. On a page like that, the empty space between the planets is not vacuum. It is careers. It is children growing up. It is the researchers who proposed a mission and did not live to see it arrive. Look at the record honestly, and one thing becomes clear. We were never stopped by money, though money was always tight. We were never stopped by engineering, though the engineering was brutal. And we were certainly never stopped by ambition. A species that flies a nuclear helicopter to a moon of Saturn has no shortage of that. We were stopped by time, only ever by time. The solar system is not far away. Neptune sits 4 hours from the sun at the speed of light. A signal from Voyager 1 takes a single day. In the scale of the universe, this is the doorstep. It is simply slow, and here is the part worth holding on to. Knowing that a spacecraft launched today might not answer its question until the people who built it have retired, or died, or been forgotten, we launched anyway, again and again. We wrote impact dates into plans decades ahead. We taught our procedures to strangers who had not yet been born. The solar system is not far away. It is slow, and we chose to wait. Right now, while you sit there, none of it has stopped. A signal left Voyager 1 yesterday and is still crossing the dark. It reaches Earth tomorrow, whether anyone is listening or not. Bepi Colombo is falling toward Mercury tonight, a few months from the moment it either arrives or doesn't. Europa Clipper is 4 years out. New Horizons is awake again in the cold past Pluto. And in a crater on Mars, sealed tubes are lying in the dust, waiting for hands that have not been trained yet. None of it needs you awake. That is the strange comfort in all of this. Things continue toward the places they were aimed at, patiently, without applause, long after the moment anyone decided to send them. And so does everything you have set moving, a kindness you have forgotten, work nobody thanked you for. Something you said to someone years ago that is only landing now, somewhere you will never see. You won't be there for most of it. That isn't failure. That is simply what a life looks like from the inside. Waiting was never the empty part of the journey. Waiting was the journey. Thank you for coming all the way out here with me and all the way back. If this reached you, a like and a subscribe is how I know. More journeys are coming, quieter ones, stranger ones, further ones. I hope you'll be there. Sleep well tonight. Nothing out there arrives quickly, but it arrives.